So we're going to look at some right triangle trigonometry today. If I am back in my unit circle, remember we said the x and y coordinate can be found via the two new functions that we talked about there, the sine and the cosine. The sine gives us the y coordinate, the cosine gives us the x coordinate. Well, like we said last time, the Pythagorean identity that came up with sine squared plus cosine squared equals 1, I can also realize that that's a right triangle. So remove the circle, like get rid of the circle, it's not there anymore. I still have this right triangle, right? There's the angle that we were talking about. There's the theta right there. So I can say that this right triangle, I don't need a circle. If I have a right triangle, I can say that this is the cosine of that angle, and this is the sine of that angle. Now, what do we remember about triangles? If we have two different triangles with the exact same angle for the first angle, the exact same angle for the second angle, that means that this third angle, we can call it beta, or whatever we want to, alpha, that this third angle is also the same, right? Because the first two are the same, theta and theta. It's a 90 degree and a 90 degree, so angle 1, angle 2 equals angle 2, so that means angle 3. So we have similar triangles. And since we have similar triangles, all the ratios are preserved. So what that means is if I take two sides from the green triangle, like the cosine, and I divide it by the sine, that ratio, how cosine compares to the hypotenuse, is also over here in the red triangle, how the adjacent side, which corresponds to where cosine was, how that compares to the hypotenuse of this triangle, right? So that's what we're talking about here, right? And then likewise, if I take the sine in this one, the sine is to 1 as the opposite side is to the hypotenuse, right? And then the sine is to the cosine as the opposite is to the adjacent. So all those different ratios, remember when we talk about with similar triangles, the side lengths aren't the same, obviously. This is obviously bigger than this, this is obviously bigger than this, but because those three angles are the same, then the ratio of side lengths are proportional, meaning they're always the same, they're always constant. So as this grows at a rate that will keep that ratio when you divide equal. Alright, so that's what we mean by proportional triangles, or the side lengths are proportional. But if you look, what we have here is the trigonometric functions, sine and cosine, and then remember this is the same thing, sine over cosine is the same as tangent. We have the trigonometric functions, the three main ones, written in terms of a right triangle. We're no longer needing the unit circle anymore. We can just talk about them as right triangles. So the cosine, remember cosine divided by 1 is still just cosine. The cosine is the adjacent over the hypotenuse. That's the cosine of this angle. Adjacent meaning the angle that's the side length that's touching the angle along with the hypotenuse. Sine equals opposite over hypotenuse. So the side opposite is basically the side the angle opens up to. That it doesn't include either of the sides that touch the angle. Alright, and then the opposite over adjacent, that's the tangent. That's, remember we said it's kind of like slope. So it's like it deals with the opposite and adjacent side to that angle, not the hypotenuse. It's not included on that one. So what we've done is we've redefined those three trig functions with right triangles instead of the unit circle. Alright, so this is the right triangle trigonometric definition of all the three main ones, and then just again notice cosecant, you just flip over the sine. Alright, secant, flip over cosine, tangent, cotangent, you just flip each other over. They're reciprocals. So remember, these are the reciprocal functions before. They're still the reciprocal functions. Alright, notice up here in big bold it says acute angle theta. The reason why it's acute is because this is right triangle trigonometric functions. Right triangles, if you got a right angle, then the other two angles have to be acute. You can't have an obtuse angle here. Okay, we will deal with obtuse values and how sine and cosine, tangent, all that are affected later on. But right now with the right triangles, the other angles that we're being given have to be acute. So there are going to be acute angles for right now. Alright, one way to remember sine, cosine, tangent, the opposite, hypotenuse, adjacent, all that is the mnemonic SOHCAHTOA. SOHCAHTOA. So SOH, sine, opposite, hypotenuse. CAH, cosine, adjacent over hypotenuse, and tangent, TOA, tangent, opposite over adjacent. So that's one way that people remember that. It helps. I remember when I went through trig, it really helped me to remember who was who initially until you get it down. Alright, you can get it down visually if you remember how it relates to the unit circle, y, x. So, but with right triangles, we can orient these things in many different ways. It doesn't have to be, the angle on the left-hand side. We can orient a right triangle any way we want to. So it does help to remember this as we make our way through here. Alright, so here we got 4 different right triangles of varying sizes, and each of the triangles theta is the exact same angle. It never changes. Okay, it's approximately 56.3 degrees. That's what's giving us the ratio of these side lengths. It's been rounded, so it says approximately. Okay, but what we want to see is the tangent will always be the same. Tangent is opposite over adjacent, so opposite is 3 over 2. Opposite is 6 over 4, which reduces to 3 over 2. Opposite is 1.5 over adjacent 1. Right, simplified. Remember to simplify when you have a decimal to get that decimal out of there. We change this to initially 15 over 10, and then we reduce it to 3 over 2. Or you can just think of doubling both. Alright, and then 4.5 to 3, same thing. Double both, you get 9 over 6, and then reduce. 9 over 6 will reduce to 3 over 2. So again, just like we talked about here, the initial definition was in a circle, a unit circle, where we can create a right triangle. But then once you have one right triangle, you can make as many as you want to. You just blow that right triangle up, and you make as many right triangles as you want. And then we use the property that the ratio of side lengths are preserved, and now the ratio of side lengths are what these functions are. Sine, cosine, tangent are ratios of specific sides in these right triangles, and so this is just showing that they're preserved if the angles are the same. Alright, now let's go through each of the 6 trig functions. We want to find each of the 6 trig functions if this is our right triangle. Alright, so we want, first of all, we're missing C. All we have is A and B. So we're going to do some Pythagorean theorem stuff. Remember, we square this, add, and then take the square root, and we get C. Alright, so if we do that, you're going to end up with C being 13. So that's the first thing we need to do, is figure out what all 3 sides are. Alright, and now we can set up sine, cosine, tangent, all the 6 trig functions. I always do them sine, cosine, tangent, and then over here beside them the reciprocals, cosecant, secant, cotangent. Alright, SOHCAHTOA. So, S-O-H, sine is opposite. Alright, opposite the angle is 5 over hypotenuse. So 5 over 13. Alright, cosine is adjacent over hypotenuse, so 12 over 13. Alright, remember sine and cosine have to be smaller than 1. Remember from the same definition from the unit circle, they can't ever have the hypotenuse. The biggest number can never be in the numerator for sine and cosine. Not the case for tangent. Alright, tangent, opposite over adjacent. So that'll be a 5 over 12. Alright, now if you do these three first, remember cosecant, secant, and cotangent are just reciprocals of these. So cosecant is a reciprocal of sine, so that's going to be 13 over 5. And then secant and cotangent are reciprocals of the other two. So there's our sine, cosine, tangent, cosecant, secant, cotangent. There's our 6 trig functions of theta. And we get the other three from the first three. Sine, cosine, tangent are the main three. You'll hear me call them the main three, the big three, a lot this semester, and then you'll hear me call these the other three because they're just the reciprocals of the first three. Alright, once again, this time I've got the hypotenuse, I've got a side length, and I don't know the other leg or the other side length. So here I need to square 3, and instead of adding, I need to subtract the other one squared. So 1 squared is 1. So that's 8, so this is going to be the square root of 8, which I can write as 2 times the square root of 2. Alright, and now that I know all three side lengths, same thing as before. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, and then flip them over. So there's the different values that I would get for these. Again, just flip the first 3 over to get the other 3. Okay, if you get a 1 on the bottom, again, you just write the number. You don't have to worry about putting that over 1 in these cases. Alright, here is something that if you did the unit circle activity that I suggested that you do, you should see all these numbers, but these are the different values you get for the first 3. There's pi over 6, pi over 4, pi over 3. There's special angles in quadrant 1. Here's sine, cosine, tangent that you should have on your unit circle, hopefully. And then here are the same things for cosecant and secant. Now notice these, if you take, like for instance, if you took the square root of 3 over 3 and you flipped it, you would get 3 over the square root of 3. Well, 3 over the square root of 3, if you rationalize the denominator, you end up with the square root of 3. So just know that these things have been rationalized to not have any radicals in the denominator. It's not necessarily wrong if you put 2 over the square root of 3. It just, a long time ago, you didn't have a graphing calculator or a calculator that could handle radicals and give you decimals really quick and easy, so we rationalized the denominator. So it's kind of standard nowadays to get rid of radicals in the denominator, but notice I didn't do that here, so it's fine with me if you leave the radicals in the denominator. But just notice this is where this is coming from. It's a quick, easy access, but again, hopefully you've got that from your unit circle if you did that activity. Alright, trig functions and their complements. Remember, since this is a 90-degree angle and the 3 angles of a right triangle have to add to 180, not just a right triangle, but any triangle, they have to add to 180. So if this is 90 and this is theta, that's 90 plus theta, and we subtract from 180, that leaves that this angle has to be 90 minus theta. Or you can think of it as, since all 3 have to add up to 90, and this is 90, that means these other 2 have to be complements, so they have to combine to 90. So since this is theta, this is 90 minus theta. Now, what does that mean? Well, think about this. This C, this is the hypotenuse. Okay? Alright, this is for theta, this is the adjacent side. Alright, that's adjacent for theta. But it is the opposite side for 90 minus theta, which is also an angle. So we have to think about the fact that there's 2 acute angles here, not just 1. Alright, and then side A is the opposite side for theta, and it's the adjacent side for 90 minus theta. Now notice here, if I find the sine of theta, sine is opposite, so that's going to be A over over hypotenuse, which is C. Well, what if I find the cosine of 90 minus theta? Well, remember, cosine is adjacent. So the adjacent side of 90 minus theta is A. Adjacent over hypotenuse is A over C. So what do we get? We get that the sine of theta is equal to the cosine of 90 minus theta. And because these 2 angles in right triangle trig, these 2 angles are always complementary, this will always be the case. That the sine of theta will always be the cosine of 90 minus theta, and likewise the cosine of theta will always be the sine of 90 minus theta. Alright, and now this holds true whether we're using degrees or if we're using radians. It's just if we're using radians, instead of 90 minus, it'll be pi over 2 minus. If we're using radians as the angle measures rather than degrees. So sine of theta equals cosine 90 minus theta, cosine theta equals sine of 90 minus theta. Now this is also true for any of the cofunctions. Notice cosine, cotangent, cosecant. So this will always be the case. The cosecant of theta will also be equal to the secant of 90 minus theta. This is a property of what we call cofunctions. So if we put in the complement of these angles, then the co-angles, the cofunctions of those particular complementary angles will always be equal. So that's what we got right here. The cofunction identities. This is your first trigonometric identity. Well, no, the Pythagorean identities were your first, but this is one of the next most important ones. So the sine of an angle equals cosine of 90 minus, and vice versa. But it's also true for the other cofunctions: tangent, cotangent, secant, cosecant. So these are the cofunctions. So each trig function, sine, tangent, and secant, has a cofunction: cosine, cotangent, cosecant, and it works both ways. You know, whoever gets to be theta, if the cofunction, meaning has the co or take the co away, of 90 minus theta of the complement will always be equal. Alright, put it in your calculator and verify it. Alright, I'm going to put our calculator into degree mode just for the time being, just to show this. But the cosine of 80, alright, and then I'm going to type in the sine of 90 minus 80, which is 10, or you can just make sure the two numbers in parentheses add up to 90. I get the exact same thing. Alright, the tangent of 40, right, and then the cotangent, remember cotangent is 1 over tangent, the cotangent of, if I put in 50, that's what I need to come up with to get 90, I get the same thing. Okay, so this is a property for any of these cofunctions: secant, cosecant, tangent, cotangent, sine, cosine. Alright, and then remember, if you're talking about radians, replace 90 with pi over 2. Okay, so find a cofunction with the same output as these values. For sine of 72, it's going to be the cosine of 90 minus 72, which is 18. So the cosine of 18, the sine of 72. Alright, and then cosecant, pi over 3. This was going to be the secant. Alright, and then it's pi over 2 minus pi over 3. Remember with the pi's I was talking about before, if we're going to figure out what this is, pi over 2 minus pi over 3, I'm going to do 1 over 2 minus 1 over 3. Alright, that's pi over 2 minus pi over 3. I've just pulled the pi out. I'm going to change it back into a fraction. I get pi over 6. So secant of pi over 6. Alright, now how do I know if this is right? Easy for this one, I just type in sine of 72 cosine of 18. Alright, what about the others? Well, first I need to make sure I go back to radian mode. And then cosecant is the reciprocal of sine. So I'm going to type in sine of pi over 3. Alright, and then this button is reciprocal, x inverse. So I just click that. There's the cosecant of pi over 3, and then the secant of pi over 6. Again, that's the reciprocal of cosine. So I'm going to type in cosine pi over 6. Oops, pi over 6. And then I'm going to flip that over with the reciprocal button. Alright, and I'm getting the same thing. So that works. So secant of pi over 6 is the cofunction of the cosecant of pi over 3.